day, students. Welcome to Bachelor of Education Senior Primary Natural Science and Health 5 for the examination of the year 2022. I'm your tutor, Christine Kaukushikongo. We start with the presentation. The main aim of this presentation is to highlight some important aspects of the modules that students are required in preparing for the examination. The content of this presentation will focus more on topics which are known to be challenging to students. Although it will not cover all the topics, it will only highlight some of the most challenging topics. It should also be noted that topics which are not covered in this presentation should not be taken as not important or as if they are not going to appear in the exam. Hence, due to time and much content for our module, not all topics to be covered, and those that are to be covered, they will not be discussed in more details. You are therefore advised to consult me on my contact detail, my cell phone number. You can either email me or call me. Then you can ask any question or make appointment for more explanation. Starting with the topic that we are considering as most challenging, we'll start with distance-time graph. The distance-time graph is a graph where we have distance on the horizontal axis, on the vertical axis, and time on the horizontal axis. Students are expected to be able to explain different sections of the distance-time graph. For example, on a distance-time graph, a sloping line shows that the object is moving. The slope of the gradient on a distance-time graph is equal to the speed of the object. The steeper the line or the steeper the graph on a distance-time graph, the greater the gradient and the faster the object is moving. On the next slide, we have a diagram representing the distance-time graph with different objects. The next concept of our discussion is speed or velocity time graphs. On the first slide there, we have the speed time graph or velocity time graph. Students are also expected to be able to explain what happened to the motion of the object at each section of the graph. For example, the first part of the graph from 0 second to 4 seconds, the object is accelerating uniformly, and then after 4 seconds, from 4 seconds to 2 seconds, that's constant acceleration. That's constant speed, which is 0 acceleration. That's a blue line. And then from 6 seconds to 8 seconds, from 6 seconds to 7 seconds, then the object is accelerating again. That's uniform accelerating because it's a straight line, showing that the speed is increasing. And then from 7 seconds to 10 seconds, the green light that shows that the object is decelerating. That's called negative gradient or negative acceleration. So the next thing that we also need to know, this slide just explains how the speed time graph can be explained. Like the speed in meter per second is always on the vertical axis, and time is always on a horizontal axis. The gradient of the speed velocity time graph represents the acceleration of the object, and the formula for calculating that it's always change in y divided by change in x. Of course, the unit will be meter per second squared. The area under the speed time velocity, the area under the speed velocity or velocity time graph represents the distance traveled. In most cases, students do make mistakes when they are asked to calculate the distance traveled on a speed time graph. It should be noted that the distance traveled on a speed time graph or a velocity time graph is equal to the area under the graph not velocity times time as a normal do. Other points to remember on a speed-time graph is that the gradient of the line is the acceleration. If the gradient is negative, that's deceleration. The flat section represents constant speed, and the area under the graph represents the distance traveled. The next point that we will discuss in our presentation today is resultant force. Resultant force can be calculated in two ways. When the two forces are pointing on the same direction, the resultant force is calculated by adding the two forces together. When the forces are pointing in different directions, the resultant force is calculated by subtracting the smaller force from the larger force. There we have a diagram that shows the forces, two forces acting on different directions. We have the thrust of 500 Newton force and then the drag. Since these two forces are pointing on two different directions, the resultant force will be 500 Newton minus 500 Newtons, which will give us 0 Newton. So this means that this car, if it's going to continue moving, it will continue moving at a constant speed, if it was moving. Then you proceed to the next topic of our interest, balanced and unbalanced forces. It should be noted that when two forces acting on the same object are equal but act in opposite direction, they are said to be balanced because the resultant force will be 0, of course. When two equal and opposite forces are acting on the object, then the object is either stationary, that is, it's not moving, or if the object is moving, the object will continue moving at the same speed and in the same direction. But when the two forces acting on the same objects are on opposite direction but they are not equal in magnitude, the forces are said not to be balanced. That's what we call unbalanced force. When there is unbalanced force on the object, then the object can either speed up or slow down or change direction, or if it was stationary, it will change the position. The next diagram shows the balanced force. On the first diagram, we have two forces, 5 Newton, pointing on different directions. If we subtract these forces from one another, the resultant force will be 0. The unbalanced force, we have 10 Newton pointing on the right-hand side and 5 Newton pointing on the left-hand side. Subtracting them will get 5 Newton to the right-hand side. Therefore, this object will move toward the right-hand side because there is a resultant force on it. Then we move to the next topic, which is extension load graphs. The extension load graph of a spring, it's a graphical representation of its extension versus applied load. This extension load graph is drawn to see how extension of a spring depends on the applied force. Then we look at the graph itself. Students should be able to label the elastic limit or limit of proportionality from the load extension graph. As indicated on the graph there, it's a point where the force and the load, the force and the extension stop being direct proportional. The spring will deform and it will no longer go back to its original shape at that point. Then there are key features of the load extension graph: the limit of proportionality as well as the elastic limit. The maximum amount a material can be stretched and still return to its original length. This is what we call now elastic limit. This point is always after the limit of proportionality. Then we move to moment. Moment is defined as a turning effect of force. Moment is a turning effect. It's a vector quantity because it has both magnitude and direction. Then the principle of moment says that moment on the left should be equal to moment on the right hand side, or clockwise moment should be equal to anti-clockwise moment. Students are expected to be able to apply the principle of moment to solve some problem related to moments. For example, we have example 1, a parent and a child at the opposite side of a seesaw. The parents weigh 750 Newton and the child weigh 250 Newton. The child is seated 2.4 meters from the pivot. Now we are supposed to calculate the distance that the parent should sit from the pivot to balance the seesaw. Now to solve this problem, we have to use the principle of moment, which says moment of the child should be equal to moment of the parent. Then we write down the formula for moment on both sides. Then we substitute the given information. For the child, the force and the distance is there, so we substitute 250 Newton multiplied by 2.4 meter equal to the force of the parent is there, 750 Newton, multiplied by the distance, but the distance is not known. So d will remain is an unknown. So we continue with the calculation, then we solve for d. Finally, when we divide, we're multiplying 250 by 2.4, we get 600 Newton meter. Then you have to divide both sides by 750 Newton to solve for d. The answer that we got, d is equal to 0.8 meter. So the parent should sit 0.8 meter from the seesaw, from the pivot to balance the seesaw. This is one of the problems that students should be able to. Then we move to pressure. The definition of pressure will also lead us to the formula that relate pressure, force, and area. Pressure is a force applied to the surface of an object per unit area. Therefore, pressure is equal to force divided by area. The unit of pressure is Newton per meter squared. Since the force is measured in Newton and area is also measured in meter squared, but sometimes the area can be also in centimeter squared. The SI unit, the standard international unit for pressure, is Pascal. And it should be noted that 1 Pascal is equal to 1 Newton per meter squared. The diagram shows the relationship between pressure and area. The relationship between pressure and area is that the smaller the area, the greater the pressure. For example, we have a high-heeled shoes. The weight of the person wearing that shoes is, this pair of shoes is 600 Newton, and the area in contact with the ground is 0.0001 meter squared. For an elephant, the weight is 30,000 Newton, and the area of the heel in contact with the ground is 0.1 meter squared. Now, to see which one exerts greater pressure, we calculate the pressure in each case. Then for the women, we have to find that the pressure is 3 million Newton per meter squared, while for an elephant it's 125,000 Newton per meter squared, meaning that the women exert a greater pressure on the ground than the elephant, since the area in contact of the shoes is smaller than the elephant. Then we move to thermal physics. Then we start with transfer of thermal energy. Students are expected to know that there are 3 different ways in which heat can be transferred, and they should be able to define each way. And then conduction is defined as a transfer of thermal energy during which medium does not move. Conduction is sensed to be more in solid because solid particles are packed tightly close together, they are in touch, so heat can be transferred faster. And conduction is said to be a little bit slower in liquid and gas because there are small spaces between those particles. Convection is defined as a transfer of thermal energy due to the movement of fluid itself, and convection happens in liquids and gases because these are the ones that can flow. Convection requires free movement of particles to occur. That explains why transfer of thermal energy via convection cannot occur in solid. So convection cannot take place in solid, but it's much faster in gas particles because these particles are fast to move and they are far away from each other, so heat can be transferred faster. The third way of transferring heat energy is radiation, in which heat can be transferred by infrared waves, and this way heat can be transferred through the vacuum. So radiation can be transferred where there is no material. Then you move to other factors that affect the rate of radiation of a body. The color and the texture of the surface. Dull and dark colors absorb and emit infrared at a higher rate compared to shine and light surface. Surface temperature. The higher the surface temperature in comparison to the surrounding temperature will result in a higher rate of infrared radiation. Surface area. A body with a larger surface area will absorb and emit radiation at a higher rate. Then you move to general wave properties. So first we start with the types of waves. There are main two types of waves, longitudinal waves and transverse waves. Students are expected to be able to differentiate between transverse wave and longitudinal waves, and also be able to give the example of each. They should also be able to label the different components on the longitudinal waves and transverse waves. Longitudinal waves. In a longitudinal wave, particles vibrate parallel to the direction of the wave. And in the longitudinal waves, there are compression and rarefaction. And in the longitudinal waves, the wavelength can be marked from one compression to the next compression. Transverse waves, the particles vibrate perpendicular to the direction of the wave. In the transverse wave, we have peaks, peak and troughs. Peaks also known as crest. So the highest point in the transverse wave is called a peak or a crest, and the lowest point in a transverse wave is called a trough. Example of longitudinal wave, we have sound wave. Example of transverse, we have light, water waves, and we have electromagnetic waves. There we have the diagram of a transverse wave where different components are labeled. Students are expected to be able to label the components correctly, more especially the wavelength and the amplitude. The amplitude is the maximum distance from the resting position to the highest point in a wave, or from the resting position to the lowest point in the wave. Then you move to the next slide. These are just defining different wave properties like amplitude and wavelength. We also need to know that wavelength is a distance, it's measured in centimeter or meter. Amplitude is also a distance that can be also measured in centimeter or meter. Then you also need to know the correct symbol for this property. Wavelength, it's in short, it's written as lambda, and amplitude you can use A. Then we have also velocity, frequency, wavefronts, and periods. The definitions are given there, the units are also given there. These are some of the terminology that are used in wave properties, and students are also expected to be able to define them as well as use them in the content. Other properties of wave, we have reflection, refraction, and diffraction. Refraction is a bouncing back of the wave from the surface or from the plane. During refraction, frequency, the speed, and the wavelength all remains unchanged. Then comes refraction. This occurs when the waves are moving from one medium into another medium with a different density. Students should also note that when it comes to waterways, as waterways move from shallow to deep or from deep to shallow, this is also known as refraction. And during refraction, the speed change and the wavelength change. It's only the frequency that remain the same. The direction also change. The third property is diffraction, which is a process by which the waves spread out as a result of passing through a narrow gap or across an edge of an object. The first diagram that we are seeing there represents the reflection of water waves. That's the bouncing of water waves. As you can see, the wavefronts represent the space between the wavefronts represent the wavelength. So we can see that the wavelengths remain the same during refraction. Only the direction that changes. The next diagram shows the refraction. This is now the movement of water from deep to shallow and then from shallow to deep. We also have wavefronts there, those straight lines that represent wavefronts. The distance between the wavefronts represents the wavelength. We can also see that the wavelength change as water waves move from deep to shallow and the other way around. This information is also summarized down there. From deep to shallow, the frequency remains the same. And then the wavelength from shallow to deep, the wavelength become deeper. The wavelength become longer. And then the speed also slow down, so student can just read this on their own. Then we have a diagram representing diffraction of water waves. This is now water waves passing through a gap. First, the wavefront are straight line parallel to each other before diffraction, but after they pass through the gap, they are now curved. Now, how they will be curved, it depends on the size of the gap. The wider the gap, the less deflected or the less curved the waves. The narrower the gap, the more curved the waves after diffraction. Then we move to another property of another example of wave, which is now sound wave. We said sound is an example of longitudinal waves. Sound is only produced by vibration of particles, therefore sound cannot travel in the vacuum. Sound travels fastest in solid and least in gas. Then other property of sound is pitch and loudness. The pitch of the sound depends on the frequency and they are direct proportional. The higher the frequency, the higher the pitch. The loudness of the sound depends on the amplitude. The larger the amplitude, the louder the sound. Students are also expected to be able to draw the waves showing the quietness and then showing the pitch, the difference in the pitch and so on. As you can see on the diagram on the left hand side, the amplitude is smaller so it's quieter. The one on the right hand side, the amplitude is larger so it's louder. The next diagram shows the pitch, the relationship between pitch and frequency. So when it comes to the frequency, we have to count the number of waves in a wave set. On the left hand side, we have just half of a wave, showing that there is less frequency there because the number of waves are less compared to the one on the right hand side. On the right hand side, we have 3 waves, so the frequency is high, therefore the higher the pitch. So students should also be able to draw a wave set on a given wave, given the information whether it is louder or quieter than the one that is given. Then we move to the next topic. It's part of magnetism, electricity and magnetism. So we start with electromagnetic induction. First, we have to define what it is. In short, electromagnetic induction is a process of producing electricity from magnetism. As we can see on the diagram there, when the wire is moved across the magnetic field, and then the wire is connected to the voltmeter or a millivoltmeter that can measure small voltage. As long as you move the wire between the magnetic field, cutting the field magnets, a small amount of current will be produced. Then the needle on the millivoltmeter will deflect, indicating that current is produced or voltage. Then there are 3 ways in which we can increase the voltage produced in this way. Induced EMF can be increased by moving a wire fast, the speed at which you move the wire across the magnetic field, if you increase it, more voltage will be produced. Or using a stronger magnet. So students should also be able that it's not about talking about strong. It's not about the size of the magnet, it's about the strength, but it should be stronger. And then we can also increase the voltage produced by increasing the length of the wire. Because if you make a coil, then if you have more turns, then there will be more voltage produced. Those are three ways in which you can increase voltage produced by electromagnetic induction. Then electromagnetic induction is applicable in transformer. Then we have two types of transformer, step up and step down transformer. The student should also be able to state whether this is a step up transformer or is a step down transformer, given the diagram or given the information. Therefore, a step up transformer converts low voltage into high voltage. Therefore, the number of primary coil, the number of turns on the primary coil are always less than the number of turns on the secondary coil for a step up transformer. For a step down transformer, it aims to convert high voltage to low voltage. Therefore, the number of turns on the primary coil in a step-down transformer is greater than the number of turns on the secondary coil. The letter NP stands for number of turns on the primary coil, NS stands for number of turns on the secondary coil. This diagram just shows electromagnetic induction, how the magnet can be moved in the coil to produce current. Now, in this case, if there are more turns, then more current will be produced. And then students should also be able to see that the direction of the current produced moves in the opposite of the force that causes it. As the magnet moves clockwise, the current direction will be anti-clockwise. The diagram shows the structure of a transformer. VP stands for voltage on the primary coil. That's now the supply, which is always AC connected to the primary coil. And VS stands for voltage on the secondary coil, which is always connected to the output. Then students are also supposed to know the ratio, the transformer ratio equation that can be used to solve problems related to the transformer. Then another topic that we should also look at is electric current. From the definition of electric current, one should be able also to relate the formula that relates current, charge, and time. Electric current is a measure of the rate of the flow of electric charge through a conductor. And then when components are connected in series, current always flows one way. And when components are connected in parallel, then the current can divide into the branches. Then we need to know the resistance and Ohm's law. We know that resistance is the opposition to the flow of charge. Ohm's law states that current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Therefore, students are expected to know the factors that affect the resistance of the wire, which is the length of the wire, the cross-sectional area, the temperature of the conductor, and the material from which the conductor is made. Then students are also expected to know the relationship between resistance and the length, resistance and the cross-sectional area, resistance and temperature. So they are stated there. Resistance is directly proportional to the length of the wire, resistance is inversely proportional to the cross-sectional area, and the resistance is directly proportional to the temperature. When it comes to the type of material, just that the conductors that are made from copper, they have low resistance because copper is the best conductor of electricity and it has low resistance compared to those that are made from tungsten, for example. There we have an example of an ohmic conductor. Ohmic conductors are conductors that obey Ohm's law. So the voltage and currents, they are direct proportional. The resistance doesn't change. Therefore, the graph is a straight line through the origin showing a direct proportional relationship. Our last topic of discussion is nuclear physics, starting with types of radiation. Alpha, beta, gamma, these are different types of radiation. And for each of these radiation, students are expected to know the nature, the property, the penetrating power, the charges, and the effects, the electromagnetic effects and the electro effects and magnetic effects on each of these. Then you also need to know that beta radiation, these are said to be fast moving electrons, while alpha radiation, they are helium nucleus, and gamma, these are not particles, they are radiation with the shortest wavelength, with the highest penetrating power and highest frequency. Then we move to half-life and radioactivity. Students also be expected to be able to define half-life and be able to find the half-life from a decay curve. For example, we have the curve here, the radioactive sample decaying over time. So in this case, we have the activity on the vertical axis and time in days on the horizontal axis. To find the half-life on this decay curve, let's look at the explanation there. Starting from the timing, if you start from 80 activity, a half of 80 is 40, so the time taken for decay, for the sample to move from 80 to 40, it takes 2 days. Therefore, the half-life is 2 days. You can also prove it from 40, a half of 40 is 20. It takes 2 days for this sample to move from 40 to 20. Therefore, the half-life of this substance is 20. That's how we get the half-life from a decay curve. Then we move to the uses of radioactive isotopes. These are just some of the uses, but students can still find more and more explanation on this. They can be used for radioactive dating, irradiation of food. They can also be used to treat food and then keep them longer. They are also used in medical application. So these are just some of the uses, but there are more uses over there. Students can find out more. Then we move to the safe precaution and handling of radioactive isotopes. The radioactive isotopes should be kept or stored in a lined box, in a lead lined box, because we know it's only lead that can completely absorb them. Protective clothing must be worn whenever one is handling them. You should avoid contact with bare skin, and you should not attempt to taste the sources. You should always wear face masks and avoid breathing in materials. You should limit the exposure time and handle the radioactive material with dogs. And you should also monitor the exposure using detectors, badges. We have come to the end of our presentation. Good luck and best wishes for your study. Be blessed.